Dear students, today we are going to discuss about sampled data control systems. Let us see. When the signal or information at any or some points in a system is in the form of a discrete pulses, then the system is called discrete data systems. So, in the case of control engineering, the discrete data system is popularly known as sampled data systems. So let us see the block diagram of sampled data control system, and in the block diagram it uses a sample and analog to digital converter, digital computer, digital to analog computer and hold circuit that all together forms the digital controller section. Then the planned or continuous time system will be there. You can see here that there is an adder. Actually it subtracts the input signal from the feedback signal so that an error signal is produced. That error signal is a continuous time signal, and the output from this digital controller is also a continuous time signal. So here E of t is the error signal, U of t is the control signal, and F of kt is the digital error signal that is shown here, and G of kt is the digital control signal. So the sampled data control system using the digital controller uses the analog input E of t. Here E of t is the error signal. So the input and output signals in this digital computer is analog signals. So that means here the digital computer is that this signal is input and output signal is this input and output signal is digital signals, but the input and output to this digital controller is analog signals, and other signals are discrete signals, okay, or digital signals. So these two signals together drive this planned or continuous time signal. Together drive this planned. That means this continuous time signal is given to this planned. So here at this point the error signal is sampled by the sampler, and here also there is an analog to digital converter. So the signal will be digitized from this section. So that digitized signal will be given to the digital computer, and the output of that digital computer will make proper code corresponding to this signal, and that will be then given to, that is also a digital signal, then it will be given to digital to analog converter and hold circuit, so that it will be decoded and it will be converted into analog signals here. So that signal is given to the planned. So the sampler converts the continuous time error signal into a sequence of pulses, and analog to digital converter produces a binary code for each sample, and these codes then given as the input to this digital computer, and that process the binary code corresponding to this digital signals and produces another stream of binary codes at the output. Then it is given to the digital to analog converter and hold circuit, and that converts this binary codes to continuous time signals or analog signals, and that signal is called control signal. That means it is given here as a control signal, that is G of kt, digital control signal. So this is the basic block diagram for the sampled data control system, and here is explanation. Input and output signals in a digital computer will be digital signals, and error signal and control signals, that is output of the controller, are the analog in nature. Sampler and ADC provided at the input of the digital computer, and DAC and hold circuit are provided at the computer output, and the sampler converts the continuous time signals to sequence of pulses. Analog to digital converter provides the binary code for each sample. DAC and hold circuit produces the output binary code or converts the output binary code to continuous time signals. And next let us see the sampling process. Sampling is the conversion of the continuous time signals or analog signals into discrete time signal, and it is obtained by taking samples of the continuous time signal or analog signal at a discrete instance of time. You can see the periodic sampling of an analog signal. Here the f of t is the analog signal. It is given to the sampler, and so that it is represented by a switch. That means whenever the switch is closed, that signal will be goes to outside. Whenever the switch is open, signal will not be there. So at the output we will get discrete instance of time or discrete signals. That means whenever the switch is open, the signal will not be there. That means a discrete time signal is obtained at the output. And here the time interval between these instances depends upon the closing and opening time of the sampler. So if f of t is the input to the sampler, then the output is represented by f of kt, where t is called the sampling interval or sampling period, and the reciprocal of t, that is 1 by t, is called sampling frequency or sampling rate. That is, we can represent it as f of fs. And here you can see the analog signal, and when we are passing this analog signal through the sampler, we will get discrete in amplitudes at particular intervals of time. You can see here, this is the discrete signal obtained here. Okay, so this type of sampling is called periodic sampling, because we are getting the samples only uniformly at intervals of t seconds. That is why we are calling it as a periodic sampling process. Next, let us see the sampling theorem. The definition of sampling theorem is a band limited continuous time signal with highest frequency or bandwidth fm hertz can be uniquely recovered from its samples, provided that the sampling rate fs is greater than or equal to 2 fm samples per second. That means we are able to recover or reconstruct the signals from the samples only when fs is greater than or equal to 2 fm. That means fs, at least the fs value should be equal to 2 fm. Then only we can reconstruct the original signal from the sampled versions. Okay. So let us see, for processing the sampled signal by a digital means, you can see here in the case of here we are using a sampler. Here we will be getting the sampled output here. So in order to process the sampled output signals by digital means, we have to convert the sampled signals into binary codes, and this conversion process is called quantization and coding. That means the process of converting the discrete time continuous valued signal into a discrete time discrete valued signal is called quantization. That is an important term. That is, quantization is the process of converting the discrete time continuous valued signals into a discrete time discrete valued signals. So that process is called quantization. That means there will be particular levels for the signals. That means there will not be continuous amplitude for signals. There will not be any continuous amplitude for the signals. So we will be given a particular amplitude levels for the signals in the quantization process. In quantization, the value of each signal sample is represented by a value selected from a finite set of possible values, and these are called quantization levels. And the difference between the unquantized sample and the quantized output is called quantization error. After the sampling process, we will be quantizing the output to convert the discrete time continuous time signals into discrete time discrete valued signals. So after that process, we have to code the signals. So the coding is the process of representing each discrete valued signal by an n-bit binary sequence, and the process of sampling, quantization and coding are performed by a sample hold circuit and ADC. So let us see the analysis of the sampling process in the frequency domain. So we are representing we are making the analysis of sampling process in the frequency domain with the help of Fourier transform. Let us see. Suppose fs of t represents the sampled version of the signals, periodic sampled version of the signals. So f of t is the original analog signals, and we are sampling this signal by continuously multiplying with impulse signals. Okay. So here we are seeing that f of t is analog signals, and the sampling process of f of t means that we are multiplying this analog signal f of t with the impulse train del t of t, that is impulse train. So that when we are continuously multiplying the signal with this impulse train, we will be getting the sampled version of the signal, that is fs of t. So fs of t is represented by f of t into del t of t, where delta is called the pulse area or pulse width. So mathematically the impulse strain can be expressed as del t of t can be represented as sigma k equal to minus infinity to plus infinity del of t minus kt. So we can represent fs of t is equal to f of t into delta into, instead of this we can substitute this one, so we will get like this. And here capital T is called the sampling period. So we can generally represent the sample, this is analogous signal and this is the impulse strain signals. You can see the impulse values are here. The signal will have an amplitude for zero duration signals. So this represents impulse strain. When we are multiplying these two signals, we will be getting the signal like this. Okay. So the frequency content of the signal is obtained from the Fourier transform of the signal. Now the signal is this one. So its frequency content is obtained by taking the Fourier transform. So we are taking the Fourier transform of that signal, that is represented by f of t, that is equal to f of omega, that will be equal to minus infinity to plus infinity f of t instead of f of t. What is the Fourier transform equation? It is equal to minus infinity to integral minus infinity to plus infinity f of t into e raised to minus j omega t into dt. And here instead of f of t we are substituting the values, that is fs of t, that is equal to fs of omega equal to this equation, and here instead of fs of t we can substitute the previous equation, so we will get this equation. So here you can see that here the Fourier transform is the multiplication of two signals. So in the Fourier transform cases, the multiplication of two signals is similar to the convolution of the Fourier transformed version of the two signals. So we can rewrite this equation as fs of omega is equal to delta by t into sigma k equal to minus infinity to plus infinity f of omega minus k omega s. So this equation gives the frequency spectrum of the impulse sampled signals. So the frequency spectrum of the signal is given by this portion, that is it is obtained by plotting the f of omega versus omega. So you will be getting this signal like this. So here you can see that f of omega is a band limited signal with a maximum frequency of omega m, that is shown here. See here, this is the frequency spectrum, and again we can see what will happen whenever the omega s, that is sampling frequency, is greater than 2 omega m and sampling frequency is less than 2 omega m. See here, you can see here is the diagram. Whenever omega is greater than or equal to 2 omega m, that you can see that the samples are separated. There is no overlapping between the samples whenever omega s is greater than 2 omega m. Similarly, whenever omega s is less than 2 omega m, you can see here that here there is some overlapping. So in the first figure you can see that the frequency spectrum of the original signal, that is this one, this signal is repeated in this case, that is repeated periodically with the period omega s. So here also there is no overlapping, and in the second case you can see that there is some overlapping, so we cannot reconstruct the signals from this value. So in order to get the correct signals, we will have to set omega s greater than or equal to 2 omega m, that is a sampling theorem. Based on this we can form Shannon formulated a theorem, that is Shannon's sampling theorem, and that states that the information contained in the signal is fully preserved in the sampled version as long as the sampling frequency is at least twice the maximum frequency in the signal. Okay, that's all about this sampling theorem and sampling process. Thank you.